Alright, hello, my name is Jared Swartz. I'm a member of the GOLD team along with Jason, Jeremy, and Simon. And today I'll be covering the root locus plotting for the voltage system for 70 to 95 volts. Today I'll be going over background, previous work, SSOC, step, sign, gOLD. I'll cover the transfer function, FOPDT parameters, root locus theory, modeling, results, and conclusions. This is a schematic diagram of our system. You have a computer that goes to a controller to a 5 horsepower 3-phase motor into a DC generator that goes to both load lights and a voltage transmitter back to the computer. Right here we have a block diagram of our system showing that the input is power percentage and the output is voltage generated. Our range is from 70 to 95 volts. This is our SSOC diagram with an output operating range in blue and an input operating range in red. The slope is a K of 2.5 volts per percent. Here we have a block diagram for the step function showing the equation in the middle is gain times e to the minus t0s divided by s times tau s plus 1 in parentheses. This is an example of a step function with modeling. And these are the results we had. We had 4 ranges we used. The first was 83 to 85%. The step up in this range was about 1.9. The step down was 1.3. For 86 to 88%, we had a step up of 1.7 and a step down of 1.4. For 89% to 91%, we had a step up of 1.8. We had a gain of 1.8, and going down we had 1.5. For 92% to 94%, we had a gain of 1.8 going up and 1.7 going down. For dead time, these are our results. We had 0.065 seconds going up for 83 to 85. Step down, we had 0.025. 86 to 88, we had 0.04 and 0.035. For 89 to 91, we had 0.065 and 0.04. 92 to 94, we had 0.04 up and 0.035 down. The time constant, we had 0.035 seconds going up, and then for down, we had 0.008 or 0.08. We had 86 to 88%, we had a step up of 0.35, step down of 0.7. 89 to 91, we had a step up of 0.25 seconds and a step down of 0.6 seconds. For 92 to 94, we had a step up of 0.22 seconds and a step down of 0.12 seconds. This is a block diagram for the sine input. We used 3 input ranges, 83 to 86% with an 84.5% baseline, 87 to 90% with a baseline of 88.5%, 91 to 94% with a baseline of 92.5%. Our amplitudes we used were 1.5% and the frequency range was 0.02 to 12 Hertz. This is an example sine output. We have a 3% change in input, a period of 16 seconds, a change in output of 4.10 volts, and a shift of 0.36 seconds. This is the graph at 0.06 Hertz. This is a sample of our gOLD plot. We found the KCU for 87 to 90% input to be 1.22 volts per percent. Our amplitude ratio was 0.82 volts per percent. Tau was 0.13 seconds. The ultimate frequency was 8.5 hertz. and T0 was 0.25 seconds. This is our bogey with modeling for 83 to 86%. Using the K was 1.3, T0 was 0.062, and tau was 0.09. This is for 87 to 90%. The K was 1.4%, tau was 0.09 seconds, T0 was 0.06. And this is our bogey with modeling for 91 to 94%. And the ultimate frequency for this was 6.9 hertz. These are our results. The observed for 83 to 86 showed 1.4, same as the modeling. For 87 to 90, this is for the gain. It showed 1.41 was observed and 1.4 was the modeling. For 91 to 94, we had 1.41, and for the modeling, we had 1.42. For T0, we had an observed of 0.24 for 83 to 86, 0.25 for 87 to 90, and 0.27 for 91 to 94. All of our modeling showed a 0.06 T0. And then for our tau, we had 0.14 for 83 to 86, 0.13 for 87 to 90, 0.12 for 91 to 94. And our modeling showed for 83 to 86 and 87 to 90, we had a 0.09 tau, and for 91 to 94, we had 0.08 tau. This is our transfer function with the CLTF function down below. We had a gain of 1.4 volts per percent, a T0 of 0.06 seconds, and a tau of 0.09. This is the root locus theory. Shows that the roots 1 and 2 equal minus zeta plus or minus zeta squared minus, or the square root of zeta squared minus 1 divided by tau. And the decay ratio is e to the minus 2 pi zeta divided by square root of 1 minus zeta squared. The effect of zeta is for zeta greater than or equal to 1, the system is overdamped, monotonic, and stable. For 0 less than zeta and 1 greater than zeta, the system is underdampered, oscillatory, and stable. For zeta equals 0, the system is undamped and sustained oscillation. Minus 1 less than zeta and 0 greater than zeta, the system is unstable and growing in oscillation. And for zeta less than or equal to minus 1, it is a runaway monotonic and unstable. This is our root locus for 83 to 86%. We found a KCD of 0.16 volts per percent. Our KC 1/500th was 0.58. Our KC 1/10th was 1.5. KQD was 2.0, and KCU was 3.1. This is our root locus for 87 to 90%. I'll go over the results here in a second. And this is our root locus from 91 to 94%. I'll also go over those results in a second. Here are the results showing our KCU values, our KQD values, our KC 1/10th values, our KC 1/500th values, and our KCD for our different ranges we use. Our system was overdampered in 83 to 86% for 0 less than KC, KC greater than, or 0.16 greater than KC. At 87 to 90, 0 was less than KC and 0.25 was greater than KC. For 91 to 94, we had 0 less than KC, 0.38 greater than KC. The system was critically damped at 83 to 86% for 0.16. For 87 to 90, 0.25. For 91 to 94, 0.38. The system was underdampered at 83 to 86 for 0.16 less than KC and 3.1 greater than KC. For 87 to 90, it was 0.25 less than KC, 4.1 greater than KC. For 91 to 94, it was 0.38 less than KC, 5.3 greater than KC. Our quarter decay was 2.0 for 83 to 86, for 87 to 90, 2.3, 91 to 94, 2.8, for 1/10 at 83 to 86%, we had 1.5, at 87 to 90, 1.76, at 91 to 94, 2.2, and our 1/500ths at 83 to 86 was 0.58, 87 to 90, 0.72, and 91 to 94, 0.93. And that is the conclusion of this presentation.